Hi everyone, and welcome to Jam Academy. In this lesson, we want to talk about the meaning of translational kinetic energy. In other words, we will talk about the conceptual meaning as well as how we can actually calculate or measure the translational kinetic energy of a moving object. If you recall kindly, energy is the capacity or the ability of an object or force to do work on another object or system. And work is done when a force moves its point of application in its direction. Another way to talk about work is the transfer of energy from one object to another. Whenever energy is transferred, work is done. So essentially, work done is the transfer of energy. But the question is, what is translational kinetic energy? In general, kinetic energy is simply the energy an object has because it is moving. That explains why we call kinetic energy the energy of motion. As long as your position is changing, you have kinetic energy. So the question is, how can we define kinetic energy in a way that we can actually measure it and calculate it in the classroom? Kinetic energy is the energy of motion, which means if you are moving, you have kinetic energy. But remember, work is the transfer of energy from one object to another. So let's say we initially have a box of mass m. The box is initially at rest. In accordance with Newton's first law of motion, this box will remain at rest until an external force acts on this box. In other words, we have to exert a force on the box in order to provoke or cause the box to move. Let's say that we then exert a force on the box F, causing the box to accelerate from rest to a particular velocity v. Now, the work done to accelerate the box from rest to a particular speed v is what we call kinetic energy. Let me say that again. Kinetic energy is equal to the work done to accelerate an object from rest to a particular speed. Let me say that again. Kinetic energy, which is the energy of motion, is equal to the work done to accelerate an object from rest to a particular speed v. Now let's analyze this critically. The object is initially at rest, so v0 is 0. We accelerate it from rest because we've applied a force F in the direction of motion to a particular speed v. What does that mean? V is equal to v0 plus at. Now we also know that v squared is equal to v0 squared plus 2a delta x. Remember, delta x is simply the distance covered, the distance traveled by the box at that particular time. Now v0 is 0, so this is just gonna be, this will imply that the acceleration a of the object is equal to v squared minus v0 squared, all divided by 2 delta x. Let's keep this in mind. Let's call this equation 1. The object accelerates. Remember, the object accelerates from rest to a particular speed v. For an object to accelerate, there must be a net force acting on that object. By Newton's second law of motion, that net force F net is equal to the mass of that object multiplied by its acceleration. This would mean that the net force will be equal to m multiplied by v squared minus v naught squared, all divided by 2 delta x. All divided by 2 delta x. Now we can rearrange this equation to give us something pretty beautiful. If you look at this carefully, we can now see that this would mean that f net multiplied by delta x will be equal to 1/2 m bracket v squared minus v naught squared. Now the question I want to ask you is, what is f net multiplied by delta x? This simply represents the net work done. In other words, it represents the total work done on the object. And the total work done on the object is equal to 1/2 mv squared minus 1/2 mv naught squared. This is a very important equation in physics. We're going to come back to this a little bit later. But I just want to remind you of the fact that the initial velocity is 0 because the object starts moving from rest. If the initial velocity is 0, then the net work done on the object to accelerate it from rest will just be equal to 1/2 mv squared. Will be equal to 1/2 mv squared. And what did we say? We did define the kinetic energy of an object as the work done to accelerate that object from rest to a particular speed v. And hence, this work done is therefore equal to the kinetic energy of that object. So Ke is equal to 1/2 mv squared. So this is the mathematical expression that will help us to calculate the kinetic energy of an object. That will help us to calculate the kinetic energy of an object. Now this brings us to the equation in red. What is this telling us? It means that the net work acting on a system is simply equal to the change in the kinetic energy of that system. Let me say that again. The net work done on a system is equal to the change in the kinetic energy of that system. This we call the work kinetic energy theorem. The work kinetic energy theorem. The work kinetic energy theorem, which essentially states that the net work done on an object is equal to the change in the kinetic energy of that object. Now I want to submit to you that this is just an alternative form of Newton's second law of motion. I can prove it to you at another time. But bear with me that when you look at this particular expression, you will notice a couple of things. One, the kinetic energy of an object, which is simply the energy of the motion, specifically the translational kinetic energy, is 1/2 mv squared. What is this telling you? One, the mass of the object is always positive, is a scalar. The speed v is squared, which means that the speed in this particular case, which means that the kinetic energy of an object can never be negative. In other words, this is always greater than or equal to 0. That is very important. The kinetic energy of an object is a scalar, which means that it has only a size or a magnitude without a direction, and it is always positive. It is always positive. If an object is moving with a speed of 4 meters per second to the right, the object will have the same kinetic energy as the object moving with a speed of 4 meters per second to the left. The direction doesn't matter. Let me say that again. The direction really doesn't matter. Now, there is an intrinsic relationship that exists between the kinetic energy of an object and the momentum of that object. Let me show you. There is a relationship that exists between the kinetic energy of an object and the momentum of that object. Bear with me that the momentum of an object P is the mass of that object multiplied by V. This is specifically the linear momentum. So this would imply that the kinetic energy, which is just 1/2 mv squared, will be equal to mv all squared divided by 2m. mv is P, so this is equal to P squared all divided by 2m. In other words, the kinetic energy of an object is equal to the momentum of that object squared divided by 2m. This is a very good equation with some important properties. Let me give you how you can encounter this particular equation. If you have two objects A and B with the same momentum, if A has twice the kinetic energy of B, then how are their masses related? Keep that in mind. If Ka is equal to 2Kb, this would mean that P squared all divided by 2Ma will be equal to 2 bracket P squared all divided by 2Mb. This takes care of this. This takes care of this. And you will realize that Mb is equal to 2Ma. Automatically, you realize that the object with less mass has more kinetic energy, and the object with more mass has less kinetic energy. These really are just some very simple, neat things that I thought that you should know. But before we go, keep in mind that kinetic energy is the energy an object has simply because it is moving. Now, the translational kinetic energy of an object is simply equal to the work done on that object to accelerate that object from rest to a particular speed v. If you have any questions, please do not hesitate to ask in the discussion forum below. Thank you, and bye-bye.